Right, Unit 3, Day 3 notes. We're going to talk about logarithms now, just related to what we did before. So the answer logarithm is an exponent. So the way I think of it is saying, what are you raising 10 to get 1,000? That's how I read it. That'd be 10 to the third power. So 10 to the third power gives you 1,000. So it's also a nice way, if you think of it that way, that's another way of rewriting it as an exponential. The base raised to the exponent equals the answer. The base raised to the exponent equals the answer. So you can change logs to exponentials. Just one quick application is a Richter scale for earthquakes. Every next value in the Richter scale is actually a factor of 10. So Fukushima was a 7.1, past Robles way back when was a 6.1. That means that Fukushima was 10 times larger than past Robles. So, anyways, all right. So it's the exponent. It's like a graph with like a log graph. Now, graphing logs, let's just start with an exponential because they're related. They're the inverse functions of exponentials. So there's a lot of things about inverse functions that we can use for any pair of inverse functions. So let's just start with the exponential. 10 to the negative 2 is 1/100th. 10 to the negative 1 is 1/10. 10 to the 0 is 1. 10 to the 1 is 10. 10 to the second is 100. So this is like the graphs we've been graphing yesterday. Horizontal asymptote goes through 0, 1. Okay. So you guys should be pretty good at that, graphing exponentials. Now, let's make a table here. This is now, if you don't see a base, that's a base 10. It's called a common log because it's very common. We use a base 10 number system. So it's saying, what would you raise 10 to get 1/100th? You'd raise it to the negative 2. What would you raise 10 to get 1/10th? You'd raise 10 to the negative 1. What would you raise 10 to get 1? You'd raise 10 to the 0 power. What would you raise 10 to get 10? 10 to the first, 10 to the second. Now, the interesting thing here is that you'll see we get all the same xy values from the exponential function, but the x's and y's are switched. And that's something that always happens with any pair of inverse functions. So we're going to actually use this in the future to help us on some other things. So that means 0, 1 becomes 1, 0. And visually what happens is when you swap all the x's and y's and you graph them, if you graph the line y equals x through the origin, 45-degree angle, it looks like the graph gets reflected across it. So this goes here. This horizontal asymptote becomes a vertical asymptote. And looks like this. It looks like the graph has been flipped across that line. That's what any pair of inverse functions are. So this is 10 to the x. This is log base 10 to the x. So we're going to ask the same kind of questions as last night's homework. I'm going to say, is it increasing, decreasing? It's increasing. Concave down. Range is all reals, negative infinity, positive infinity, interval notation. Asymptote is now vertical line. X equals 0. So we're going to add that to our answers tonight, just like last night. So this is what a log graph looks like. But you could always get it by flipping a y equals exponential graph across y equals x. So Natural log is just log base e, so you could do y equals e to the x, which goes through 0, 1, as horizontal asymptote y equals 0, and then put 1, 0 instead. So instead of keeping track of the y-intercept, we're now keeping track of x-intercept. X equals 0. So there you go. So it looks pretty much like a log base 10 graph. Log x, that's the same thing as log base 10 of x. So I don't know. I find if it's been a while and you don't remember what the graph looks like for log, you always just start with exponential. Which is pretty easy. And then flip 1, 0, x equals 0. You can even draw this line in here if you want, and it looks like this. So that's how we do it. Now, this one's interesting. You'd say, well, this would be the inverse of y equals 1/2 to the x. But yesterday we said, well, that's the same as 2 to the negative x. So you could start with 2 to the x. And then flip it sideways. Right? Y equals 2 to the negative x. And then flick that across y equals x. Now, the best thing to do is to get the x coordinate from the x-intercept from the y-intercept, get the vertical asymptote from the horizontal asymptote. Anything that's y becomes x. X, y's get switched. Now this graph's going like this, so this graph's going to go like this. Another interesting thing is if your graph crosses y equals x, then the other graph is going to cross it at the same place. We're going to say this is decreasing concave up range is negative infinity, positive infinity, asymptote is x equals 0. It's a vertical line. So there you go. This graph, natural log is log base e of x. So you could graph y equals e to the x, which you should remember because you've been doing it forever. And then use that to get your other graph. So change the y-intercept to the x-intercept, change the horizontal asymptote to a vertical asymptote, graph this line on there if you want. So this is what natural log of x looks like. Now, the negative on the outside flips it upside down, and the plus 1 moves everything up 1. So we're just keeping track of what was the x-intercept. Now it's kind of in the middle of the graph. And we make the dark version of the final answer, just like we did last chapter with trig graphs. And now we're going to say it's decreasing, concave up, range is negative infinity, positive infinity, asymptote is x equals 0. So putting that on our answers tonight. So that's the idea. That's how we do it. Now, a couple other issues that are important when dealing with logs. The domain. The domain of a function is all the x values you're allowed to plug into it that actually produce answers. So things like vertical asymptotes are not part of the domain, or you can't take square roots of negatives, and so forth. You can only take logs of positives. So can't be negative, but also can't be 0. Now, if you just look at the basic graph of a log graph, we were just doing this, right? This is what it looks like. And it has this vertical asymptote. So of course it's not defined as 0, but you also notice it doesn't exist over here. It only exists for positives. So the graphs make sense with this. So this one right here, the domain is x has to be positive. But we're also going to write it, usually probably going to want to write it in interval notation, 0 to positive infinity. Same thing, better for what we've been doing. This one right here, you can show the work. Well, the inside, what's inside the log or natural log or whatever, has to be positive. So it means x has to be greater than 2. Or 2 to positive infinity, which is better. Okay? But they're going to get a little more complicated. The inside has to be positive. Well, write that the inside is positive. Now you got to solve that. Oh, that's a rational inequality. This is unit 1 stuff. Yeah. Right? You guys remember how to do this? Line check. So x equals 0, x equals 3 is a vertical asymptote. We do a number line. They're open dots. Whatever comes in bottom is always open dot. Top's open dot because it doesn't know what we're equals to. Test the value. Watch out for bounces. Test far right. Positive, positive, true, false, true. And so the answer is the domain is negative infinity to 0, union 3 to positive infinity. The other way you can say is x is less than 0 or x is greater than 3. But you're going to have to do some of the work from, and you might be like, oh, I thought you said we couldn't do negatives. Well, if you plug these negatives in, it actually results in a positive inside the natural log, which is what's important. Is that what's inside is positive. That could come from negative x values. Just depends. But we're going to be doing work from chapter 1, unit 1. Now, log rules. There's a bunch of rules for logs that you guys should have learned before algebra 2. So, one deal is being able to rewrite them in exponential. B to the a equals n. Natural log of x is the same thing as log base e of x. There's a rule for combining logs together. If they have the same base and they're being added, you multiply their insides. If they're being subtracted and they have the same bases, they got to have the same bases. Then you combine them together and you divide the first base, what's in the first log by the second log. There's something called the power rule, which allows you, if there's an exponent on what's inside the log, you can bring it out in front as a coefficient. What do you raise b to get b? 1. What do you raise b to get 1? 0. What do you raise e to get e? 1. What do you raise e to get 1? 0. Anytime you have log of any base of 1, it's always going to be 0. And then there's this other rule that can help you with getting answers from your calculators. You have logs with different bases and stuff. You can change the base by saying, okay, well, this is a natural log. I want it to be, that should be log base b. It's a natural log, or it's a log base b. I want it with a different log, like log base 10. You say, okay, well, log of, with the new base of what was inside divided by log with the new base of the old base inside, it happens in here. So on your homework tonight, there's a couple different kinds of problems. There's two things that you want to try and get to happen. So you either want to get a log equal to another log, single log, same base, because then you could set their insides equal to each other. It's kind of like the exponentials where you make the bases the same, then you set the exponents equal, right? So as an example, on tonight's homework number 19, looks like this. Now, you see a bunch of logs, so you want to eventually get to a single log equals single log. So you got to use some of these rules. Now you got to bring this inside first, 2 to the 4th. And now you can combine those two logs together into a single log. This is going to be 16 divided by 3 because it's minus. Now you can set the insides equal to each other. Right? So the other scenario on tonight's homework is if you don't have a bunch of logs that you're going to make equal to each other, maybe something like problem 16, you have log base 27 of x equals negative 2/3. Well, I'm not going to make this a log equal log to set the insides equal. So if you have a single log equal to a number, so if you have a log equal a number, you want to change it to exponential form. Take the base of the log, raise it to the right-hand side, equal to the inside. And then you could solve this. So you'd say, all right, well, let's do the 1/3 power first, which is cube root. So you always want to do the denominator first. So cube root of 27 is going to be 3. And then 3 to the negative 2 is 1/9. So something like that. So these are the two different kinds of problems. Log equal number or log equal log. And those are the two kinds of strategies you're working towards. So, all right, there you go. Try the homework tonight. Check your answers.